Arden. I hope you're there. Arden Warner is a particle accelerator physicist and the founding partner of Natural Science LLC, and is the inventor of the systems used for electromagnetic remediation of oil and chemical spills. He investigates the fluid dynamics associated with hydrocarbon and chemical spills on water and designs environmentally sensitive mitigation and remediation techniques. So he'll be speaking to us today on electromagnetic remediation of oil and chemical spills. Arden, are you ready to join us? There you are.
Yes. Hello, good afternoon or good morning, depending on where you are. Thank you for having me. Let me get my screen ready to share, but I wanted to say that I want to introduce today technology based mainly on the physics of how we study oil and in its environment with water and other surfaces. We spent quite a bit of time developing technology that it remediates based on the forces that allow these things to combine or not. Let me just share my screen. Okay, I hope everyone can see my screen.
That's good.
Yes. So this technology is essentially based on studying the nature of the forces that are involved in assessing how oil and water behave in different environments, and allowing these forces that combine oil or allow oil to combine, and studying these forces at very fundamental levels. The fluid dynamics, I don't go through the details. What I decided to do today, let's see if I can advance my slides, is to introduce the EMOP, what we call EMOP and MAT technologies. These are a suite of technologies that work together to clean oil and chemical spills. It's what we call electromagnetic remediation technology. So I want to go over the fundamental concepts without going into all of the physics of the dynamics of the equations, but I have a lot of video to explain some of that. We want to look at the unique features and some advantages, the fluid dynamics and the external forces, the engineering applications and some of the implications, some dispersal methods really quickly, and how this technology applies in a variety of different situations. So let's start with what we call EMOP technology and the absorbent technology. I'll describe them here broadly. And let's see if I have a pointer. So the electromagnetic mitigation methods use essentially magnetic fields. And so it's really a system and a method for remediating oil and chemical spills on water and land. It uses electromagnetic pulses and time magnetic fields to produce forces that move, lift, and transport oil and other hydrocarbons as well. Materials used are environmentally safe and reusable materials, and we'll explain what that means. They're natural materials. We've been studying materials that exist naturally in nature and using those. I will also describe the absorbent. I really enjoyed the last talk about the summarizing absorbents. And here's a category absorbent that I didn't see it at the very beginning was discussed, but magnetic absorbent technology. So the idea here is that absorbents can be retrieved magnetically. We can enhance the absorbent, not the absorbency, but the collection efficiency. And also, if the system is done right, the thing that makes it magnetic can also be used because it combines with oil to increase how much oil you actually collect. So it's a really interesting product and solution. So it can be manipulated magnetically to trap and remove environmental spills, including oil, fuels, chemicals, PCBs. And it can be used on land and water. So I'll start by describing this technology because these two play an important role together. So a brief description. So hydrocarbons form a very unique bond with micron-sized magnetite particles. They render the substance magnetic in the presence of magnetic fields. Viscosity effects become enhanced, and we'll say something about that. This system that we're using provides a method to confine, attract, move, magnetized fluids. So we use essentially solenoidal coils and other magnets to provide magnetic field gradients, because the forces that these things feel are proportional to the gradient of the magnetic fields. The system collects fluids within the reach of the magnetic field, so we can collect oil that's basically at the surface or anything a little bit below, a foot or so below. That's the range of the magnetic fields, depending on the power of the system. It can be used in conjunction with our magnetic ramps, which we will discuss. And the separation process is interesting because it's based on magnetorheological effects, which I hope we can describe. And we can target hydrocarbons, it targets microplastics, it targets benzene at a micron scale. So I want to show you this system in operation and some results. So essentially, what I want to describe here is the fact that particles in oil can be manipulated, and that the attraction to the oil is very, very strong. The affinity is very good, is very high. And you can actually remove 100% of these particles at the end. This bond is basically based on van der Waals forces, and the fact that on water, for example, I'm using water as an example because on water, it's a very interesting colloidal mixture where you can manipulate the fluid, but as soon as the surface tension is changed, you can actually extract the particles. So the particles are essentially held by these van der Waals forces. Recovery could be 100%. We've done extensive testing on many oil types to verify that these forces are consistent based on the particle size. The solution, in general, behaves very Newtonian-like when it's in water, and that allows us to model these systems in a very special way before we design the systems that we use. The particles have a very high affinity to hydrocarbon chains, and this provides us to gather and trap these fluids, and it also introduces something we call confinement. Oil in water normally expands out under its own forces based on its viscosities and external forces, but when these particles are embedded, that rate slows down significantly, and so we want to describe that a little bit more for you. So the magnetorheological effects are essentially are the effects that allow a fluid to become very rigid in the presence of a magnetic field. Magnetic particles that are in a fluid, once a magnetic field is applied, they actually line up in the direction of the magnetic field. And orthogonal to the direction, it becomes very, very rigid. And so that allows you to lift it. It allows it to reject water, and it allows you to move and separate the fluids and the particles from the oil when the surface tension changes. That helps us to increase the extraction efficiency and reject water from the EMOP system that we will describe. One of the things I mentioned is that when fluid is in water, for example, it will expand out under its own viscous forces. But when we add these small particles on a micron and nano scale, the particles have an attraction to each other. They have an attraction to the hydrocarbon chains. The van der Waals forces play a very important role here. And you have this confinement. So without the particles, this test oil here would expand out under its own forces. But with the particles, it stays confined. And this is good, especially in closed systems, but it also has an effect in outdoor systems where it depends on the external forces and the nature of the magnetic forces that we apply. The particles that are held in the solution do not come out even when the oil is poured into water. The particles actually stay with the oil. They actually seek out the oil. They actually find a very strong place in the oil. And then we can use magnetic fields. And this is in a large tank of 4,000 gallons of water here. But you can see even by hand that we can extract and pull the fluid. So it's not a magnetized fluid. The particles are added to the fluid via what we call a seedling process. And the amount of oxide we use is of the order of about 0.5% by volume. And this combination is susceptible to magnetic forces. We then pulse magnetic fields longitudinal magnetic fields, the fields have to be shaped because the particles will follow the field lines. So by training the fields, by designing fields that are tapered and that we control, we can then move the oil on water in that case, so that the water becomes really a transport medium. And then we couple this magnetic system to ramps and go through a separation process. So we seed the oil and we apply a magnetic force and it pulls in the plume. And this demonstration just shows it from a top view. But the point is, I want to make sure that the system does in fact pull oil in without seeding the entire plume. So you don't have to go out and seed the entire spill. We have white papers on our site that describes the details that might be missing here if this looks mysterious to anyone, and it goes into all the physics and the details and the modeling. So the way what we've done is built systems based on magnets, special magnets with special fields that are longitudinal. They have a gradient, meaning that the magnetic field increases along the axis. A magnetized fluid will flow into this system and it will try to get to the maximum field. This is a pulse field, so there's a force causing the system to pull all magnetized items, all magnetized product in the direction that you want it to go. And this is a model of how the fields would move and how the fluid will be pulled through the system. So this is essentially an electromagnetic boom, essentially. Instead of a passive system, we're using magnetic fields. And the idea here is that the forces are well understood. And because it behaves in a very Newtonian way, we can model these systems in a complex way to get the details using Navier-Stokes equations. But I thought it would be a little bit to describe those here. But we can also use rather Newtonian dynamics to describe the forces involved and how they apply. And then essentially, once we design the right type of magnetic fields, in this case solenoids, the solenoid fields are along the axis, and the fluid will flow along the axis, and we manipulate a system using these solenoids. So here's a model with just the particles that accounts for all the dynamics of oils of various viscosities. So each particle here represents a magnetic particle, a small nanoparticle or micron-sized particle, and it also accounts for a small volume of oil. And as we pulse magnetic fields in a fluid, even when there's wave action, external wave action, the magnetic fields form potential wells that travel, a traveling wave, so to speak, that pulls the fluid along the axis. And that's the principle behind the electromagnetic boom. This system was tested on larger scales, and we found that the efficiency was very high, 97.2% at separating oil from water at a third of the power of the system that we use. And the system improvements that we've designed since the test can give us greater than 200 gallons of oil per minute for fluid in water. Here's a quick demonstration showing the system at a test at onset, and I'll speed this up a bit here, but so essentially the oil is put in, and the magnetic fields are turned on, and the oil follows essentially the magnetic field lines. This is a view from the bottom, and you can see that the oil is moving and it's following the field lines. We've increased the speed of this video slightly just so that we could advance it. But you can see now that the oil is following and it's moving in a laminar way. So we want to maintain the laminar flow of the oil, and that helps to reduce water. I just want this to complete, and then I'll show a top view of this system. So at the top, you can see how the fluid moves towards the magnetic field, and it increases its velocity as it goes, and it then couples to a magnetic ramp. And at the base, water is highly rejected, and the iron oxide and the particles are extracted, and we can separate the oil from the water if you want, just by adding a magnetic field to this system. So this is a very efficient way of grabbing oil from water and in closed and open systems. So here are some of the properties. I want to move on, but it's an active technology that uses magnetic fields. Surface and subsurface collection of spills on water can be achieved. It's a probe for oil, and I didn't show that, but these particles that we described will fall through the water and only stop when it encounters oil. It's environmentally benign particles called the particles of magnetite. Magnetite is just like natural in nature, and it's out in sand and igneous rocks and so on, and most of it's recollected. You offer confinement properties. There are magnetorheological effects that allow you to separate and reject water, and it works well on cold water and oils, because as viscosity increases, it becomes more like a solid, or approaches more of a more viscous oil, and that works very, very well. So there's some unique features in terms of the particle sizes, and the particles are stable, and there's ways to combat wave action in that the system can be aligned so that waves can push and assist the magnetic fields. So I wanted to say a few words about how we disperse the particles, but essentially they are dispersed through low velocity nozzles and special spreaders, and we can discuss that. There are questions, but the main thing is that there are rheological effects and so on that we depend on in this system in order to advance. So now I want to go quickly on to the magnetic absorbent technology. So I'm introducing here a magnetizable hydrophobic fibrous organic absorbent that absorbs normally about a gallon per pound, depending on viscosity. I'm going to describe a non-leaching, even on increased pressure. It holds the absorbed material within the cellular walls. I'll describe what that material is in a bit. It's essentially a sphagnum, peat moss, dried to a certain specificity. But by combining electromagnetic effects with this absorbent, it proves that it can be more efficient and becomes recoverable, and you get increased collection efficiency. And one very important feature is that these particles are held in place with the absorbent, and they're working independently to also attract oil. And we'll show both a discrete way of recollecting it and a way using a ramp. So here's the absorbent, magnetizable absorbent, and here I show a demonstration where we pick it up with a magnet. So there are many natural hydrophobic organic materials, such as soil humus, which is peat. They have fibrous and act as ionic exchangers. So we take advantage of this. They exchange either positive charged ions or cations or negatively charged ions in their interaction with some substances. And these fibrous materials also combine well with nanoparticles and micron size particles, especially electrolytic oxides and magnetite. There's data about how the absorbency of a peat moss, for example, increases with the amount of moisture in it. Actually, peat moss is very hydrophilic when it's greater than 60% moisture. And when it's less than 60% moisture, it's quite hydrophobic. It absorbs hydrocarbons very well, PCBs and chemicals, and it's also non-leaching. So we looked at these products under microscopes, and here you see what the sphagnum looks like, the peat moss looks like magnified. And here are the oxide particles, and you see how these particles, they're really, really small. These are 30 micron scales here, but they cluster together due to electrostatic forces. And in the presence of the ionic exchanger peat moss, it clings to it very, very tightly and it coats it. This does not stop the cellulose membrane itself from attracting or absorbing, and it absorbs, there's enough oxygen inside for the absorbed product to biodegrade within it without, even though this product itself is already biodegraded. So here's a video showing just a sample of how that absorbent works, and I'll and the other video is just a model. So let me go back to show that one. Why doesn't that go? Anyhow, yeah, we'll come back to that one. The idea here is that I can't get any of them to show here. Just bear with me 1 second.
And Arden, we have lots of questions waiting for you, so.
I'm sure, yes. Oh, am I towards the end? How much time do I have left? I can't see the clock.
You're at 0 time.
Okay, so there is a couple of methods for retrieving this. We did a test where we can pick up the absorbent using electromagnetic ramps. And since we are at 0 time, we will run one more video before we end here and leave and open for questions. But this is showing how the system can be used not just for oil spills, but for cleaning water using the same principles that we described, where we utilize all these magnetic properties to remove oil from water, and we let the system run over a period of time and see how it cleans oil from water. And I will say thank you for your attention, and questions are certainly welcome.
Thank you, Arden. Yeah, I think it's a really interesting approach. I don't know much about it except from what you just told me. I'm glad to see that you got some test time in at onset. Lindsay, what other questions and comments do we have for Arden?
Lots of questions. First from Susan Caralla, is EMOP used in place of skimmers?
It should be used in place of skimmers because it's a different technology altogether. Skimmers are based basically on also electromagnetic forces actually, but this uses electromagnetic forces at the level, at the micron scale, where we actually target the oil directly. Skimmers rely a lot on surface tension forces and can collect a lot of water. These surface tension forces are also electromagnetic in nature, but what we've done is to use these electromagnetic forces at a level where we control them. And so the particles are coupled to the oil, which couple to the magnetic fields. So this is a very different technology from a skimmer. A skimmer will also provide a lot of agitation because it's a moving mechanical part. This, as you see, is based on magnetic fields. You can't see them moving, but the magnetic fields are there. And another important thing is that the magnetorheological effects allows us to reject water at the interface between the two magnetic systems.
Great.
Lindsay, maybe you can consolidate some of those other questions.
Yes. A couple from Susan Caralla. Are the magnetic particles reusable, and is the system commercially available?
Yes, to both questions. The magnetic particles are reusable. They're magnetite. They're just recycled. They don't degrade. Magnetite is already rusted, so it doesn't rust any further. Electrolytic iron oxide is slightly different, of course, but we collect those as well. Commercially available, yes, we are building systems to need. We are looking at systems for closed systems, for external systems, for applying this to other technologies for water reclamation, for oil and gas applications in cokers and so on. So based on a need, we are designing these systems for that. But the idea, the physics has been solved, and we're very, very happy with the concept.
And one more question. How far from the system will the oil be drawn in?
Right, that depends on the power of the system. This system that we tested at OMSET was a 2 kilowatt system. We use it at a third of the power. Particles will come in from a foot away or more, and we can increase the magnetic field. So it depends on the strength of the magnetic field, but that's something that's really a question of power. And that will be the limitation, right? The amount of kilowatts power you want to use per system, but you can move the system towards the as well. The system doesn't have to sit stationary. The system can pull, so you should take the system into the plume rather than, and then let it do its work and keep moving it in.
Okay, thank you, Arden. Lindsay, could you move those remaining questions over to chat so that Arden can track that and answer those questions within chat?
You can also email me, and the absorbent is available in copious amounts and stuff like that. We didn't get into that as much as we would like. The time was short, but please email me and we'll answer all your questions or put them in the chat.
Thank you, Arden.